Okay. Hi everyone. Welcome to our 73rd session of the MedAI Group Exchange. This week we have Houcemeddine Turki with us to present his research on empowering biomedical informatics with open resources. Houcemeddine is a medical student at the University of Sfax, Tunisia, and a research assistant at the Data Engineering and Semantics Research Unit. His research spans several interdisciplinary fields, including biomedical informatics, library and information science, semantic technologies, open science, and applied linguistics. Thank you, Houcemeddine, for joining us today. Before we start, could you tell us when you want to take questions?
Yeah, as we go, I can't take any question as we go.
Okay, sounds good. So let's try to make this session as interactive as possible. Without further ado, let me hand it over to Houcemeddine.
Thank you. I am honored to be here today, actually, to talk a little bit about my work across these years about biomedical informatics using open resources. Yeah, a brief introduction about me. Well, I have had an Associate of Science in Pre-Medicine from the University of Sfax in 2018. And I am currently an MBBS student since 2018, but I am an average student, so I am not that good. But recently, I have been registered in an online university, and I am studying there computer science. Before that, I was mainly self-taught. Despite that, I have been a research assistant in Data Engineering and Semantics Research Unit, and I have had several positions in community-led consortiums or societies. Well, I have been mainly a board member of Wikimedia Tunisia and Wikimedia Library User Group that are both groups that are related to enriching Wikipedia and other Wikimedia projects such as Wikidata, Wikimedia Commons, with kind of Tunisia-related topics and libraries-related topics. So that's it. Despite that, well, I have been granted several awards. So I have been funded for my research by the WikiCredit Grant Initiative, by the Wikimedia Foundation, and by the Ministry of Higher Education and Scientific Research in Tunisia. So I am not actually a former research assistant there, but despite of that, I have achieved something in biomedical informatics. And the reason behind that is mainly open resources that can allow you to get better things, to get better results for your work, and to achieve better outcomes in your projects. Well, we just talk about that and how I did for my journey with using open data and open resources for creating biomedical applications at a low cost, because I'm not funded. I don't have a salary, but I had the grants later to actually further my research. But at the beginning, it was not the case. And so I will show you how I did that. So I will show you a brief context about why this is important. I will show you the free resources I'm using for my research, the considerations that I am aware of where I do that, and the applications that I have developed, as well as some future directions we are thinking about for the moment, about how to broaden this initiative in Africa, where scarce funding exists. Well, to get things short, well, as you already know, human development in Africa is very actually poor. Well, only 9 African countries achieve high human development, where 31 African countries have a very low human development. So that's not questionable. Well, when we see biomedical machine learning research in Africa, this is a study that I am working on now. So it is an ongoing study. Probably I will publish it this year. It's a pretrend. So you see that most of the work is done by 5 countries only, and that most of that research was catalyzed by the COVID-19 pandemic. So before the COVID-19 pandemic, there was practically no research in biomedical machine learning for the African countries. Well, consider the research topic as well. They are typical research topics. They are just conventional ones. So ones about using convolutional neural network, support vector machines, image segmentation, k-nearest neighbors algorithm, and something like that, actually to do basic things such as image analysis, text analysis, practically classification of text and of diseases. So that's the main thing. So there is nothing special and customized about research in Africa. So the current situation is characterized by a lack of regional spread, while North Africa covers 77% of the work, and Egypt and South Africa are leading the research there. There is a lack of innovation. Conventional research topics are already implemented, and they are just repeating that more and more. There is a poor development of breakthroughs and customized application to the African context. There is a huge lack of resources, poor funding, the need to upskill African human capacities and scholarly infrastructure. So that being said, so African scientists need findable, accessible, interoperable, and reusable resources to get things done, because they don't have the means to do their datasets and their infrastructure themselves. Well, in this context, there were some community-led initiatives to further this movement in Africa, where there were some self-organized communities for machine learning for healthcare, like Sisonke Biotech and Roya for computer vision, basically. And there are some scientific society-backed communities for biomedical machine learning, like the ASBCSAB COSI, which is about bioinformatics machine learning research, and the Africa, that is about biomedical imaging in Africa. And there are some NGO-driven communities, such as the Wikimedia movement affiliates. So that's the way actually Africans are getting together to form a kind of coalition and start working for developing machine learning application in healthcare, where there are also some corporations like InstaDeep and Lelapa AI that are mainly community-centric. So they are interacting with the community. They are organizing conferences like the Deep Learning in Daba. They are kind of developing some contests for machine learning enthusiasts, and they are actually sharing data sets, inviting people, catalyzing the community here in Africa. And there are some research structures that are mainly working with the community, like Basira Lab for computer vision, Rail Lab for reinforcement learning, data engineering and semantics, to which I belong, and Cohere, which is an international community-led research structure. Yeah, so all of these people are aware about the importance of free resources and are actually trying to do their best actually to use them and make benefit for the African community based on this kind of resources. So let's get through the resources that these people try to use and that I have been using for years now. So the first resource that came to the mind of any people here is the Wikimedia projects. They are a set of open and multilingual resources where anyone can contribute, edit, and adjust data. There are many kinds of projects. The most common one is Wikipedia, of course, that is the encyclopedia, but there are other stuff. There is, for example, the Wikimedia Commons, which is an image repository. There is Wikidata, which is a knowledge graph, an open knowledge graph, and they are accessible using plenty of stuff. There is the user interface based on MediaWiki. There is the MediaWiki API and the REST API. There is some Python library, for example, the PyWikibot, the Wikibase integrator for Wikidata, the WP tools for Wikipedia. The query endpoint, there is Sparkle for Wikidata, SQL for Wikipedia, user statistics, so etc. So actually, Wikidata, to cite it, is very interesting source that can be used because it is a structured knowledge graph. In fact, all information there are structured in the form of triples: subject, predicate, and object. For example, here, Behçet disease, instance of disease. Like that, this kind of representation, this information can be queried actually to get customized outputs based on the information that are included in using Sparkle, for example, or using an API, etc. So the second thing that comes to the mind of everyone is the NCBI resources. And they are a set of freely accessible knowledge resources related to biomedicine and molecular biology. Many kinds of projects are there. Literature databases,
I'm
genome
sorry,
databases, gene databases,
internet
API, and
not...
the Python library that we use. Yeah.
Sorry, I'm sorry, the internet is not very good, so I think you got interrupted for like 5 seconds, but it sounds good now.
Yeah, I can repeat this.
Yeah, sure, go ahead. Thanks.
Yeah. So the second thing that comes to the mind of everyone is the use of the NCBI resources. And actually, these are a set of freely accessible knowledge resources related to biomedicine and molecular biology. There are many kinds of projects, literature databases, there are genome databases, gene databases, clinical databases, protein databases, chemical databases, and they are accessible using user interface that is that can be accessible easily, the Entree API, and there is a Python library that I always use to process data from NCBI resources that is called Python, and its use is very intuitive. All right. Then there are some anonymized patient databases that can be used. Actually, I don't know if you are familiar with Mimic. Mimic is actually a database. Actually, it is more than a dataset of the electronic health records of thousands of patients in university hospitals. So it can be used for research purposes. It can be processed. It includes semi-structured information. You can kind of make applications based on that and test your project ideas. So it's a very good stuff. Also, there is this MIA resources, XNAT MIA resource that includes hundreds of images, biomedical images with DICOM specifications. So you can find many images, many biomedical images, many MRI images, many CT scan images for a huge number of patients, and it is maintained in Netherlands. So I think that this database too is a good thing. And if you search, you can find more than these two datasets, the databases actually. All right. Another way to get data actually is the use of data repositories. So database involving thousands of self-published medical datasets. We have Zenodo, Figshare, Gaggle, the UCI machine learning repository, the Hugging Face, etc. And many of them are described by data papers in journal like Scientific Data and Data in Brief, and they are accessible using user interface and API. But probably you can use Python libraries like request and URL-lib to kind of ensure the reproducibility of what we will do with the data. So from the beginning, the Jupyter notebook that you are using, for example, can get the data from the repository and make all the processing on it. Yeah. Another thing is big data. And big data is important and exists anywhere across the internet. We have the social network interactions, for example, Facebook, Twitters. There is search trends like Google Trends data. There is IoT data, for example, the output of IoT devices that can be searched for in search engines like Shodan.io. And there are scholarly big data that is about user statistics and downloads and sharing of scholarly publications. And what is good about this big data is that it has a huge volume. It is characterized by its variety and veracity and velocity and value. These characteristics can allow us to use this data actually for tracking the epidemiology of certain diseases based on the behavior of the users online. This is what is called infodemiology. It can also be used for the recommendation of several biomedical tasks based on what we see online. Another interesting kind of input data is the semantic resources, where semantic resources are structured databases that can be intuitively read and reused by humans through a human interface or download, and machines using Sparkle or API. Well, in these resources like Wikidata, the statements are in the form of triples, where these semantic resources can be used for a variety of stuff. It can be used for data modeling, reasoning, validation, interoperability, etc. There are multiple semantic resources. Well, there are the open knowledge graphs that exist in the linked open data cloud, and that includes, for example, Wikidata, Wikipedia, OpenSys, There is also the Open Biomedical Ontologies, or the OPO Foundry, that includes ontologies like disease ontology, gene ontology. And there are some ontologies for handling biomedical information like DICOM for radiology and FIRE-EDF for patient data. And there are some semantic web standards like RDF Turtle that can be used for handling structured data. Yeah. So besides all this data, actually, it will be interesting also to see what we can get to actually ameliorate our development process. And here, actually, we kind of can look for free software and code that can enhance our project and let us achieve more in a shorter time. Where source codes and software tools can be freely provided by open source product websites, code repositories like GitHub, package indexes such as PyPy, the Python package index, and they have kind of very useful applications. Well, these software and codes can be used for big data management and storage, data collection, processing, analyzing, and visualization, particularly machine learning, for example, health relational database management, DevOps and MLOps, etc. Also, there are some cloud resources. People who are suffering from the lack of hardware can find some cloud resources online for free, where that they can use for actually developing their applications, where there is a user-friendly list of resources available at Free4Dev database. Yeah. Another thing that is interesting to think about is the reuse of the output of robust systems. Well, most of the people have learned about ChatGPT, and actually developing a thing like ChatGPT requires a large language model. And the development of large language model requires actually billions of hyperparameters. And this costs money and is not affordable, particularly in Africa. So instead of thinking of developing this big thing, maybe we can think of using its API if it is free of charge. Yeah, so that are the main kind of data and software and code resources that I am using. Well, when using them, actually it should be kind of it should be a careful choice for how to combine this kind of resources. We should care about several things actually to have this kind of things work. Well, the first thing we have to think about is the dependency analysis, where dependencies can exist for software tools, program, and even data models and schema. For example, you see on the right, there is this import thing, and they are calling several libraries. So we should be aware of that when using, for example, a Python library, for example. Or also, for example, if we are using a Shex schema, probably it can be actually dependent on other ones, like this import thing. So maybe we should consider that. There are many types of such requirements. There's the def-use dependency, the call dependency, the write-write interaction, the write-read interaction. the read-read interaction, and all of that should be actually considered when making the choice of using an open resource, particularly Python libraries. Well, the dependency analysis actually depends on two things. Actually, the resource compatibility and the version compatibility. For example, for a Python library, some of its dependencies can be not working for a newer edition. For example, there is one of the dependencies of a Python library had a critical change recently, and so probably it will no longer work for supporting the Python library you are using. So in this context, maybe we should analyze these dependencies and actually choose the most stable kind of Python library and resources when working. The second thing is scalability. And here, by scalability, we mean that probably we will begin small when working on the project, but with time and with success, we would like to let our project bigger and bigger. And so this is what is called scalability. So scalability is how to let your small project work on a bigger scale. So you have to consider several things: network usage, CPU usage, memory usage, throughput, response time, etc. The third thing is the user experience and the interface. If you are combining many things and you let the thing become complex and its use very complicated, probably it is not a good solution. So you should combine your open resources in a way that lets your application user-friendly. Yeah. Other fact to consider, and that many people don't look at, is the resource compatibility. In fact, several licenses are more private use. This the liability. You should develop your application based on open resources in a way that is that lets your final product not biased and unfair, that lets your application explainable, robust to adversarial attacks, respecting privacy and data security. It should also attribute its attribute credit to its sources, and also it should be appropriate for the application, for the purpose of the application. Yeah, when talking about explainability, actually explainability is the fact that you are using several algorithms to process your data, and so the final result should be explainable in a way or another. And so there are three types of this explainability. There is the pre-modeling explainability. This means that that you understand the data, you know how to develop the data based on that, and you choose for your input variables based on that. Probably some feature engineering too. There is also the explainable modeling that is about how to choose the right, for example, neural networks and machine learning architecture that is appropriate for your application. And there is also the post-modeling explainability, and this works when you get the result. And this is done through the explanation of why you got some results true or false based on several explainability algorithms. For example, adversarial attacks, for example. Yeah, so that's after getting to take into account these considerations, we can now get through the application that I developed based on these open resources. Well, the first application I have been working on is the knowledge graph-based dashboard for biomedical applications. So the principle is simple. I get data from multiple resources. I use them to actually enrich my knowledge graph with information that are integrated in a way and another. I actually use an ontology to actually kind of model my data and do some semantic agreements between the different heterogeneous resources. I also use some shapes like shakes or shackle for shape-based validation of the data. I can also use some logical constraints that are implemented in Sparkle or SWRL to actually intrinsically validate the data. And then I can use Sparkle or API actually to get information from this knowledge graph and process it, for example, using intuitive algorithms, bio-inspired algorithms, or some front-end algorithms for better visualization. And then I have a dashboard. That dashboard can be used for many purposes that I will discuss later. Well, the good thing about having such a dashboard is that because it uses the RDF dump of the knowledge graph, and it is basically built using the embedding of Sparkle queries or API requests. So this kind of dashboard can be updated in nearly real time. So as the knowledge graph is updated, the application is updated. And so we kind of can obtain using this method a kind of interactive dashboard that can be used for various purposes. Well, just a word concerning the intrinsic validation. Well, actually, shakes and shackle verifies the layout of the knowledge graph, where the consistency rules in Sparkle compares two statements to validate them comparatively. And so the property statements in SWRL, it verifies only the inconsistencies at the level of one statement. So we need each one of them because they have different roles. And actually, they are interacting together, as you see here, so that the knowledge graph can be validated from different perspectives. Well, let's go now to the real life examples I have developed for this kind of applications. Well, I have developed, for example, Wikidata-based COVID-19 dashboard. My team, not me, has also developed heterogeneous social network-based dashboard for identifying COVID-19 related trends in Tunisia. There is also the ORKG-based systematic reviews and meta-analysis thing. There are also FHIR-driven EHR-based automation of clinical trials and medical education and epidemiology. There are also a dashboard for exploring the entities and arguments in COVID-19 scientific literature. So let's go and see them one by one. The first example is the Wikidata-based COVID-19 dashboards. Actually, this is my work, actually. Well, what we do is that me and many active members of the Wikidata communities have developed bots and algorithms to get things from biomedical resources, for example, open biomedical ontologies like PubMed, PubMed Central, etc., and they integrate them into Wikidata. And then using Sparkle, they are actually building Sparkle-based dashboards, actually to visualize COVID-19 related knowledge in nearly real time. So actually, all the data is verified using checks, the entity schemas, and the Wikidata actually structured knowledge is actually organized using Wikidata properties that are structured in RDF2. So that's it. Well, after months of work, we actually succeeded to represent different kinds of biomedical entities. We have scholarly articles, the outbreaks in each countries, the tracing apps, the proteins, the genes, the taxons, the biological processes, the symptoms, the medical specialties, the related diseases, the chemical compounds, the clinical trials, etc. So all that is represented and actually are related to each other using a bench of semantic relations. For example, main subject, part of, drug used for treatment, symptoms, health specialty, cause of death for the people who have died because of COVID-19, etc. And as you see here, well, as Wikipedia actually coverage of COVID-19 progresses, Wikidata coverage of COVID-19 also progresses. So because Wikidata and Wikipedia are related due to the fact that they are both maintained by the Wikimedia Foundation, so there are some people who have been active members in Wikipedia and in Wikidata at the same time. And they kind of created a workforce that kind of succeeded to represent all the kinds of information about the disease outbreak in a short time. And so that being said, the information that is included in Wikidata can be easily reused to actually get a real-time kind of overview of the pandemic, how it evolves, how it is represented, what are its characteristic from a clinical medicine perspective, etc. So as you see here, we have several dashboards have been developed, and because the Sparkle endpoint of Wikidata uses the Blaze graph as a software, so actually we can actually generate a whole bench of visualizations for the data. So for example, we have this bubble chart, we can do bar charts, we can do graphs, we can do many kinds of visualizations. And the good thing is that the visualization that we have here can be embedded in a website using iframes. So it is easy to implement a dashboard that is based on Sparkle queries, and actually it will work and it will be updated without any human intervention. Yeah, the second example my team have been working on is the heterogeneous social network-based dashboard for identifying COVID-19 related trends in Tunisia. So the principle is simple. We are collecting posts from Facebook about COVID-19, and we are storing them in a knowledge graph in RDF formats. Then we are detecting their language, and we are later generating a topic model for the COVID-19 related trends by language. So that's how it works. And actually, to represent the social interactions about COVID-19 in the database, we are using an ontology that is called SNOWL, and that we have developed for this context. And this ontology actually kind of can actually homogenize posts and interactions from different resources like Facebook, Twitter, and YouTube, and actually assign generic properties for each type of information. For example, instead of likes or dislike or retweet or share, it will only be one kind of property for the kind of similar namespaces in the three social networks. For example, instead of retweet and share, it will be only share, and that's all. Yeah. The third application is the ORKG-based systematic review and meta-analysis. And for those who do not know, ORKG stands for Open Research Knowledge Graph, and it is developed by a team in Germany called the TIB Hanover. And that team actually developed a knowledge graph that represents the findings of scholarly publications in the form of triples as RDF. And it uses, for example, research, the publication data from Crossref, data software, etc. And it uses as well domain-specific concepts actually to describe the findings of the publications. And then after representing the information about the findings of scholarly publications, the data can be used and queried using Sparkle, and actually can be used to generate a dashboard about the publication related to the same topic, as you see here, for example. And that being said, it can be used to actually do some living systematic reviews and meta-analysis. By living, I mean systematic reviews and meta-analysis that can be updated in real time. Another project that is ambitious, but actually it has not developed very much throughout the years, is the project of developing electronic health records as a knowledge graph, where all information about any clinical data is represented in the form of triples. Well, there is a project called FIRE RDF, and I am a member of the FIRE RDF subcommittee at the W3 consortium. And that team actually is developing an ontology in OWL that can be used to drive such structured electronic health records. Well, the principle is simple. Well, actually, when this FHIR EDF is developed and used to actually create the clinical knowledge graph of a given hospital, well, hospital departments will enrich that knowledge graph with their patient data. And then there will be an intrinsic validation as usual, shape-based validation, mainly using checks. And as well, we can use Sparkle because it is in RDF. So when you use Sparkle, we can generate dashboards that, for example, about epidemiological studies, about clinical trials, for example, for medical education for the students. For example, what are the symptoms of a given disease? There can be a dashboard for these students to know about what are the main symptoms about a given disease, actually for educational purposes. And also there is that API, and that API can be used to interact with local copies of external resources like OpenFoundry and Wikidata. And this can serve to find further readings about the conditions that are existing in a given department. It can be used for extrinsic validation of the data. For example, if there is a drug interaction, it can be detected using through comparison with external resources, and for data reason. So that's a very ambitious project. Probably it can be it can be a new era of medical practice if it succeeds. Well, for the moment in Tunisia, we are unfortunately not doing that. We are actually having semi-structured electronic health records that is done by the informatics, the center of the Ministry of Health in Tunisia, and that electronic health records is based on Oracle database, and it is enriched and validated and queried using PLSQL, which is a query language with a procedural language. And so even though we have that kind of ordinary electronic health record database, we can also adapt what we have as an application to the context of that typical EHR system. For example, if we have semi-structured EHR as a relational database that is driven by a relational model, we can use an SQL to actually generate such dashboards. Why not? And I think that we are currently thinking actually of going in that direction during this summer. Another real-life application in this context is the exploration of the entity and arguments in COVID-19 scientific knowledge. At this time done by a French team from IRIA, which is a very huge research laboratory in France related to computer science. So actually what they did, they got the COVID-19 open research dataset. They actually they have done some named entity annotation, and they have stored that as an RDF. So after that, they are using Sparkle actually to generate a dashboard of the keyword mentioned. They are using a graph actually visualization to visualize the keyword co-occurrence network. They are kind of generating some tables using Sparkle, etc. So it is kind of good thing. And it worked also for people in French-speaking countries, because they kind of find it very easy to use that kind of dashboard to actually get the latest news and know about the dynamics of the disease and the pandemic in quite a very real, a near real time. Yeah, but that kind of projects can actually suffer from several problems, mainly related to how to annotate the thing. Actually, there are three types of semantic annotations. There is the concept-based annotation, there is the action-based annotation, and there's the sentence-based annotation, as you see here. And so the kind of how to assign relations and how to span the entities actually depends on the preference of the end user. So that's why this kind of applications can suffer from several inconsistencies. Well, despite that, this kind of project can be useful to create actually COVID-19 node graphs. In fact, we can extract the entity associations. Entities in the same excerpt are considered associations, and then filter that based on bibliographic metadata. For example, you eliminate the paper with a limited level of evidences like letters, editorials, etc., and keep only articles and reviews. You can also confirm the relationship through keyword and abstract analysis. You can consider very common association and actually eliminate non-common ones. And you can add the relation to the knowledge graph later and add the papers, including the association as references. So I have worked for that on here. These are my publications, actually. You can see them for reference. Yeah, the second application I will be talking about is the knowledge-based systems for processing biomedical information. The principle is simple. We collect the data, we pre-process it using a first ontology, then the output of that pre-processing will be the input of the second phase, which is the data processing that is customized to the application of, to the target of the application, using the second ontology, and then the end user result will be a recommendation, for example, a classification, etc. So the real life examples I will be talking about briefly, there is the evaluation of the accuracy of biomedical image classification using ontologies, recommend their medical tourism destination based on the interaction of their social network connections, recommend their scholarly publications about the COVID-19 social trends for a given population, and biomedical relation classification based on the mesh keywords of scholarly publications. When concerning the evaluation of the biomedical image classification, we have two kinds of classification. We have the monolabel classification and we have the multi-label classification. For the monolabel classification, we actually compute the accuracy, generalize several classes, and then we compute the accuracy. Well, there is two types of results here. In fact, if the confusion actually is between two elements having the same parent class, actually the accuracy will be better. However, if the confusion is between two elements having different parents, actually the confusion will be worse. And this this method works very well with CFAR 100 because its labels are derived for WordNet 3.0. And WordNet, as you know, is a taxonomy. So you can if you have the label of a given entity, you can find its parent very easily. The second application is related to the multi-legal classification. Well, actually, many people actually develop fuzzy confusion matrices for multi-label classification. However, using feature-based semantic similarity measures and several rules, you can actually find the closest predicted labels and expected labels for every confusion. And by that, you can actually create some precise confusion matrices that are better than the fuzzy ones that are used currently. These are the rules just for information. We are using WordNet and the Rodriguez measures for the semantic similarity measure, and we are getting actually good confusion matrices based on that. The second applications we have is the recommendation of medical tourism destination based on the interaction of the social network connections of a given user. Yeah, I will finish in 2 minutes. Actually, that's not a problem. Yeah, actually, what I was saying is that we get the user information. We actually generate an ontology for the user interest based on his posts and shares and retweets, for example. And then using that ontology, we calculate the semantic similarity between the user and its trusted friends and its friends in order to actually find the closest friends of that user. And so based on what we get as closest friends, actually we find their interests, we model their interests, and then using an ontology for medical tourism, we actually find out what are the characteristics of the medical tourism destinations that are most likely to be chosen by the closest friend of the user and consequently by the user. And as you see here, using our method that uses some ontologies, we achieved better results than the methods that are that have been used in the literature before. Yeah. Anyway, third application is about recommending scholarly publications about the COVID-19 social trends for a given population. What we do is that we get social interactions about the Tunisian population about COVID-19 from different social networks. We use a COVID-19 related vocabulary from Wikidata to filter what we get from social networks so that we only keep COVID-19 related posts. And so using Snow ontology that I explained before, I actually homogenize this data and store it in RDF. And then we process it using ADA. We get topics, topic clusters, and for each topic cluster, actually we have keywords, and we formulate these keywords into a PubMed search query, and we actually get the most relevant publications related to the topics that have been evoked by Tunisian people in social networks during the COVID-19 pandemic. And this allowed us actually to address several misinformation attempts, etc. Another project, and this is the last one, is the biomedical relation classification based on the mesh keywords of scholarly publications. What I did is that we consider the mesh, each mesh qualifier for a PubMed publication includes actually a heading in red and the qualifiers in green. And the green thing actually can correspond to a facet of the heading. And so when we have the association of two mesh keywords in a given publication, actually the association of the qualifiers can let you know what to expect as the relation type between the subject and the object, as you see here. So what we did is that we generated actually a list of relations between mesh keywords from Wikidata, because Wikidata is aligned with mesh. And so we searched for the association between subject and object, and we get the mesh qualifiers for the subject and the object of the relations we extracted. And then we generated the table of the association between the matrix and between the subject qualifiers and the object qualifiers. And we stored them in a dataset called mesh to matrix. This kind of matrices are assigned relations, the relations from Wikidata, and their superclasses as well. This means the meta classes of biomedical relations or semantic relations between biomedical entities. So we using that database, we apply machine learning models, and we use some accuracy measures actually to find out if it works or not. Well, third generation of mesh matrix, we actually kind of generated around 190 relation types. And actually we generated around 46,000 matrices for the relations. Yeah, concerning the results, actually we tested our assumption on SVM, D-model, and CNET, and we found out that all of them performed well with 195 relation types, which is a breakthrough in biomedical relation classification, as well as in the 5 superclasses classification. When then we applied something called integrated gradients on the matrices to find out if all the features actually are kind of this are behind the choice of the given classes or not by the algorithms. What we found out is that there are specific kind of features that are letting the algorithm make the choice, not all of them. And this means that we can further optimize this application, and this is what we envision to do in the near future. So one idea we think about to optimize this work is to actually, we found out that this kind of blue area corresponds to symmetric relations and taxonomic ones. So probably we can get it from the matrix and mainly use the blue area actually to classify taxonomic and symmetric relations, and use the green, the gray one actually to classify non-symmetric relations only. In conclusion, in regions with scarce capacities, free resources can be life-saving for biomedical informatics research and development ecosystem. Successful applications reusing free resources to drive biomedical applications have been recorded, particularly during the COVID-19, and more emphasis should be provided on the importance of free resources in developing biomedical data science. As a future direction here in Africa, we think of developing more accessible African health datasets, and we think of organizing our machine learning and health community by building and bootstrapping initiatives across the continent. And also we think of developing some tools to make African health research more discoverable using some semantic applications. All this is done using a community called Sisonkebiotech. If you are interested to join it, here is the website. It is sisonkebiotech.africa. You can join. It is open for everyone to contribute. Thank you very much. Now time for questions, if you have one.
Thank you so much, Houcemeddine, for the presentation. Before we open the floor for questions, let's all give him a round of virtual applause. Thank you for the great presentation. It's very interesting to see all these open source resources in Africa, also like the amazing line of work that you have done. Is there any question from the audience? I actually have a question about the dashboards. You show a lot of like real life examples. So I wonder if there's a like an open source link or like URL where people can actually access the dashboard, and just curious what it actually looks like.
I can share many links actually. Well, there is actually some tool called Schoolia.
Mm-hmm.
Yeah, Schoolia is the tool, is dashboard that uses bibliographic data in Wikidata and actually generate a real-time bibliometric dashboard, the profile for the scientist or the institution.
Sounds good. Would you be able to share your screen or just to see what it looks like?
Yeah. So
maybe share your screen.
Yeah, I will share my screen again.
Okay.
Yeah. So actually, I can type my name, for example. Yeah. So for example, Houcemeddine Turki, and you see, you click on that. Yeah, it shows my image. All these are Sparkle queries actually. You see that these results.
I see. Yeah.
My publication. This is a Sparkle query. Actually, you can click on the Wikidata query service to see it, to see the query itself.
Oh, you can. Oh, I see.
You can see it. The number of publications. As you see, it plays a graph, and that's why it can generate outputs as visualizations. So you have number of publications, number of page, topic scores, the topics of authored work, the topic work matrix, the uses, the venue statistics. So I have 3 publications in Journal of Biomedical Informatics.
Yeah, this is super cool. Okay, thanks so much. Yeah, I think everyone who is live here or like watching the YouTube later, feel free to access this website and try it out.
Yeah, I will share it in the chat actually. Yeah.
Any other questions from the audience? Okay, if not, thank you everyone for joining us today. We will upload the video of the talk to our YouTube channel later, and we'll see you next week. Thank you.